question 1, we're asked to find the Thevenin equivalent resistance and voltage. So a Thevenin equivalent circuit external to RL, this guy. And there's no method specified, so it's up to us. And we know we learned mesh, we learned super mesh, we learned nodal, and superposition. And then we also learned source conversions. Now the first thing that I want to do when I look at these circuits is I want to see if I can source convert them, because that's usually the easiest thing to do. If you can do it, it's really quick and simple. So here I have an 18-volt source series with a 3 ohm. I could turn that into a current source with a parallel 3 ohm, but then I couldn't do anything with this because it doesn't have a series resistance in it. And even if I did, I would have this resistor in the way. So source conversions are off the table for this question. But I need to find a Thevenin equivalent. So the first thing I'll do is I'll start off and find my Thevenin equivalent resistance with respect from point A to B with this removed. When I want to find my resistance, if I have a current source, I'm going to remove it from the circuit and leave open terminals like it never existed. But if I have a voltage source, if I have a battery in here, I'm going to short it. I'll draw a straight wire shorting each source. And then I'll have RL removed, and I'll look at what my circuit does now. So if this was point A and this is point B, I'm going to travel through the circuit and map it as it is now with RL removed. I'll leave point A, and I'll get to this point, and I see I break 2 directions. And I have an 8 ohm here and a 3 ohm resistor here. This 3 ohm resistor goes right back to ground, back to point B, and this 8 ohm continues on, gets to this point and breaks 2 more directions. And I have 10 ohms on one path and 0 on the other, a direct short. And this circuit now looks like this. This 10 ohm is shorted. Now I only have 8 and 3 parallel. 8 times 3 over 8 plus 3 gives me 24. 24 over 11, or 1 over 8 plus 1 over 3 gives me 24 over 11, and that is equal to 2.182 ohms. Now I need to find my Thevenin voltage. Those are the 2 components for an equivalent circuit: voltage and resistance for a Thevenin, or current and resistance for a Norton. In this case it is a Thevenin, so now I need to find my Thevenin voltage, E Thevenin. So to do that, it's the open circuit voltage across RL. If RL was absent, even if RL were there, you would have that voltage. That would be the voltage across RL, but open this up, pretend it's gone, and you have a meter, and you're measuring the voltage across these points with these sources in here and the circuit functioning. We can't use source conversions, and so we look at what else we can do. What would be the easiest thing? If I did nodal, I would have VA up here, VB, and whatever I found for VA would be the voltage at point A over here. And I would see that VB is actually equal to -12, and so things would get, I wouldn't have to do a matrix, I would just need to do a little bit of algebra. But I noticed one other thing in the circuit that makes it very easy to solve with mesh. Superposition would be straightforward. It's always pretty straightforward. But mesh, in this case, is a very simple process. These are my two mesh currents. This is an amperage value. And I'm going to travel through this circuit, and I'm going to look at the first sign that I see. Just for this method, the methods of analysis, if you look at the first sign of the polarity of each component, look at the first thing that you see. When current is flowing this direction due to this mesh current, I'll start my mesh 1 equation, and I travel from the bottom left where I usually start, and I see -18 plus a voltage. I need a voltage. These are all KVL equations, but I don't have it. I have 3 ohms and an unknown mesh current, which multiplied together would give me a voltage if I knew what this were worth. So I'll go ahead and I'll say 3M1, 3 times this current, plus 8M1. I keep going. I see -12 first thing, and it all equals 0 when I get back to the point that I started at. Now, what made this very simple is the fact that I don't have a resistor on this branch here, and so I have no unknown voltages. I have a known voltage, and there's no resistor here, there's no unknown voltage, there's no differential in currents that I have to contend with. And so I just have pretty well solved on my mesh 1 current. I have 8 plus 3 gives me 11M1 equals 12 and 18, that's -30, and I'll move it to the other side and I get +30. And then I'll divide 30 by 11 to find mesh 1. 30 over 11 yields 2.727 amps. Now, I'm looking for E Thevenin. That is the voltage from ground to point A. From ground, because it's B, but essentially that's the voltage from here to here as well. So what do I need to do to get there? I need to find all the voltages and the sources and drops in this branch. So this is what I'm looking at. I found my mesh 1 current. I don't even need to deal with the mesh 2. I just need this current and this resistance to find a voltage. So this 2.727 amps multiplied by 3 ohms gives me a voltage of 8.182 volts across this resistor. So now that I know that this is 18 plus here, negative here, and I have positive, negative if current is flowing this direction. When this was mesh 1, and mesh 1 is 2.2727 amps. The voltage across this is going to be 8.182 volts. Now, when I'm doing a KVL, when I'm looking at KVL not in the and I'm not doing a method of analysis, me personally, so I only use the first sign when I'm doing a method of analysis because when I don't have to have a negative voltage drop when I'm going through here, because voltage drops by nature should be negative, but when I don't do that, I don't have to distribute negatives here, because when I define mesh 1 and I have a differential I have to distribute, it just makes the problem easier. But when I'm doing an actual KVL going down a branch, I look at the second sign. That gives me the increase in voltage. So I was at 0 and I increase. I'm at positive 18 here because this is the positive terminal of the battery. Now I have a voltage drop of 8.182. And so if I take 18, so here's my KVL. KVL from ground to this point, or KVL from point B to point A. I see negative 18 or positive 18 volts. I increase 18 and then I drop 8 volts. And so the difference between the two, 9.818 volts at this point. This isn't a true, this is a KVL across this little section. It's not a KVL loop. If I went all the way around, I'd have to set it equal to 0. I'd be at 0, I'd start out, and then I'd end at 0. This is just for this little section. It tells me the voltage here. So now I just found VA, and I found E Thevenin. So E Thevenin equals 9.818 volts. And R Thevenin is here. This question said find Thevenin equivalent resistance and voltage for the network and draw the equivalent circuit. So those two answers I need. Now I need to draw the circuit. This is a positive voltage up here. I just said that right here. And so A is the more positive point. This is 9.818 volts. This is my Thevenin resistance. It's also equal to the Norton resistance. You find them the same way. And now we have a voltage source, an accurate depiction of a voltage source with an internal resistance, and an equivalent circuit to RL, whatever we put in here. Whatever, we could put anything we wanted to in this point, in this circuit right here, in place of RL, and it would behave from the point of view RL. This is what the circuit looks like. You can say this is a black box. You don't know what's in it, but it acts like this. And that's the whole current sources. If you want to know about current sources, I'll tell you. But current sources don't exist in real life. They're made of other circuitry. You have to have electronics and stuff to make a current source. That means that a current source is not an accurate depiction of the true circuit. And so it doesn't matter what the actual circuit looks like. You just need to know how it behaves. And then that's what these equivalent circuits are doing. From the point of view of RL doesn't care what this looks like, how many batteries or resistors is in it. All it knows is what's happening to it, and what it sees is this. The total resistance from the point of view of RL is the Thevenin resistance, and the voltage that it sees is, well, it depends on the current, but the voltage of the circuit from the point of view is this, the Thevenin voltage. So here is our Thevenin equivalent. And the application of these equivalent circuits, in the reason that you're learning this, if you're mechanical, you might not care, but you might regret it later on in your studies. Maybe senior design, you'll be wishing you'd paid more attention. But if you had to design a circuit and you needed a certain a specific something or another, and you wanted it to have different, if this resistor wasn't working for you, whatever you had in here, if you were doing this on paper, you would have to, if you wanted to solve for the voltage across this resistor, the voltage drop, you'd have to take this problem and work it through with mesh or whatever you wanted to use several times, every time that you wanted to swap this value. But if you get it down into an equivalent, you can do that on paper very simply with this voltage and this resistance. Now this question says, when RL has the resistance of the Thevenin equivalent, find the voltage with polarity across RL. This one says find the current through RL in the same situation, and then find the power in the same situation. So when RL is equal to 2.182, I just replace, so I don't know what this is, but I know that whatever I put in there will have it'll have the characteristics dependent on this circuit, which is a representation of this circuit. They'll behave the same way. So when it says that RL has the same resistance as R Thevenin, it just means that you have two of them. And when you have this condition, we skipped over it in class, but when you have this condition, you have max power transfer. This resistance is the max. If you have any higher resistance than this, equal to this, you're going to have a drop in power, because you want if you wanted the maximum power that you could deliver to this load, you would want the resistance equal to this, and you would end up with max power. But now we have this equivalent circuit, and we put a resistor in it, and we can calculate everything we want to know about this circuit. It's a basic, simple series circuit, one of the first things we learned. We have 2.182 plus 2.182, sum of the resistances in a series. Just multiply it by 2, and I get RT equals 4.364 ohms. Then I know ET is 9.818 ohms, and so now I can find IT, one of the things that it asked us to find. So 9.818 divided by 3 point, did I write that? 4.364. I have ET over RT gives IT. So this divided by this equals 2.25 amps. Now that I have this current, that was one of the things they asked us to find. Find current, part C. So that is an answer that we wanted to find. I'll circle that. I across RL, so IRL equals 2.25 amps. I'll circle that instead of this because IT, if you don't know, you haven't specifically defined that IT is equal to, just for clarity on your answers on your test or homework. And now we have current across a resistance. So I times R gives voltage. So this 2.25 times 2.182 ohms gives a voltage of 4.91. So VRL equals 4.91 volts. And then, so we wanted to find current and with direction. So here, now we'll find our direction. The polarity of the voltage, positive, negative of this battery. If the battery is the only thing here, the polarity is dependent on the battery. It's going to be positive up top, negative on the bottom, or you can think of it like this. You have current leaving the positive of the battery, flowing across and going to get back. Current flows from positive to negative in our conventional theory, and so positive is on top. Now there's current direction too. So voltage, positive up top, negative on bottom, and the current is down. And now part E here asks us how much power would be delivered to RL if RL were equal to 5 ohms, which is that application part I was telling you about. If I didn't get the output that I wanted here, I wanted something else. I'm going to test a 5 ohm in here, because if I put this 2.18 in here and it's not acting the way that I wanted it to, I'll try the 5 ohm, see how that does. So that's what I'm going to do here with this equivalent circuit, rather than try and solve this all again. I'll have 2.182 ohms, our Thevenin resistance, and our Thevenin voltage of 9.818 volts, and 5 ohms here. So now 5 ohms plus 2.182 ohms gives an RT of 7.182 ohms. And we know that that is flowing this direction across this resistor. And so now we have so we have a total voltage we have a total resistance ET equals 9.818 volts. IT equals this flowing down, and its value is 9.818 divided by 7.182. And we have a total current flowing through this resistor of 1.367 amps. Now, what's power? Power is E times I. Power is also two other things. Power is I squared times R, and power is E squared over R. But I like to keep things simple and just say power is E times I whenever I can. And so I times 9 point I need to find my voltage first. I get so caught up explaining it and I forget where I'm at. So I have a current and a resistance. Multiply this by 5. This is my current. Multiply it by 5 ohms, and I'll have the voltage across this. So this is the current flowing through, 1.367 times 5 ohms yields a voltage drop of 6.835 volts. And now I know voltage and I know my current. Take this number, my voltage, and multiply it by current, 1.367, and I end up with 9 power of RL equals 9.344 watts. And I'll double check this. That is all correct. Now I have that answer. So I had this, this, and this. These were all part A. This was B, C, and D. I'm missing something. I'm missing power here. I need PRL. This was D. Always go back and make sure that you answered everything. This was E. So here we have power across this RL, in this case 2.25 amps times 4.91 volts. PRL equals 11.048 watts. There's a solution to this problem. We'll go to the next one. Now this one says use nodal specifically. We can't get away from that. Now if it didn't say that, first thing that I want to do is look and see if I can use a source conversion. If it didn't say that I had to use nodal, source conversions would be, well, let's see what we need to find. Okay, well, it depends on what you need to find. If you want to do source conversions, you could do that. You could take this and turn it into a voltage source. You could take this and turn it into a voltage source. And then you combine those voltages in series, and you would end up with a, you could combine See, you alter the question, the problem in a way that makes things difficult to find these values. I need to find current through the 4 ohm, and I can't do that after I change this into a voltage. I can't find, so nodal here, you could do it with source conversions, and that might be the best way to do it, potentially. But here it specifically says use nodal. So, first thing I want to do, I do nodal, is define where my voltages are. This is 0, my reference, and ground extends all through here. Everything here is ground. It's all the same point. I could bring all these 4 parts together to one point and just one single little ground, but then those drawings are a little bit harder to read. So, and then this is all one connection, and this is all one connection. I'm going to call this VA and this VB. Now, I'm finding, so I just need to, I'm not finding an equivalent circuit, so I just need to find individual values for different parts. So it's just a normal process. Do VA. Here's my equation for VA. When I do nodal, I say that VA is the greatest voltage. The voltage at this point is the highest in the whole circuit. And so all of the, it's kind of it's a weird way of saying things, but you're saying that all of the current is going away from VA in all directions, completely violating KCL, which says that it has to come back in somewhere. But for this method, the way that I do it, VA is the greatest voltage in the circuit. And so if current is leaving VA and going through this 4 amp source, which says that it's going this direction, I'm going to say, I know that I'm wrong, but I'm going to say you're a liar, and I'm going to make it negative. So the first term here, -4. Now this one, these are current equations, this is KCL. So I have a current leaving, an unknown current, but I have a voltage and I have a resistance. So what is that current? It's voltage over resistance, VA over 2. Now here, I'm at this point, current is leaving this direction, and it's telling me what I want to see. It's going away from VA, so I'm going to count it as positive 2 amps. Now here's where things might get tricky. We have a difference in voltages. We have VB here and VA here, and the voltage across this is the combination of the two. It's the difference between them. Now if we say that VA is the greatest voltage in the circuit, currents are all leaving this direction, means that the voltage across this has to be VA minus VB. And so if this voltage is VA minus VB, the voltage over the resistance yields VA minus VB over 4. And it's all equal to 0. And this part is what helps me not violate KCL, because I know that I'm going to be wrong somewhere. But I'm not finding currents, so I'll never know. I'm just finding voltages. And so I'll simplify this take this. This is 1/2 VA. I'll condense this a little bit. This is 1/2 VA. And this is VA over 4, which is 1/4 VA. This is VB over 4. And that's the only VB term I have. It's negative, so minus 1/4 VB. And then I have minus 4 plus 2 equals 0. Combine these. 1/2 plus 1/4 gives me 3/4. 3 over 4 VA minus 1/4 VB equals, this becomes -2, and I'll move it over, +2. Now that's my first nodal equation of the two that I need. In that last problem, we were given VB if we had done nodal because we had a battery sitting there. And if we had a battery here in place of this current source, we would know the voltage VA. It would just tell us automatically, and we'd only need an equation for VB, and we could plug in for VA. But now we do VB. If I could write it right, VB. VB over 5 gives my, first I said that VA is the greatest voltage in the circuit, and all currents were flowing away from it. Now I'm switching things up, and I say that VB is the greatest in the circuit, and all the currents are flowing away from VB. And so if that's true, then VB over 5 gives me the current going this direction. And VB over 20 gives me the current here. Now here tells me, I'm saying that current is going out, but it says that it's going in, so I'm going to say that's a -2. So -2, and then I have this differential. VB is the greatest, it's higher than VA. The difference between the two is VB minus VA. That's the voltage across this resistance. So when I want to find that current, I take that voltage, the combination of the two, VB minus VA over 4, and it all equals 0. I have 4 elements on each node, so I need 4 parts to each equation. Now I have 1/5 VB plus 1 over 20 VB plus 1 over 4 VB minus 1 over 4 VA minus 2 equals 0. Now condense that down, and I have 1 over 5 plus 1 over 20 plus 1 over 4 VB. I'll go ahead and write my VA out here because I'm going to have to set up a matrix, and I need my VAs out front. -1/4 VA plus 1/2 VB equals, move this 2 over, +2. There's my other equation. Now I want to set this up in a matrix. I'm going to make a 2-part matrix with 3 over 4. -4, -1 over 4, and then a -1 over 4 and a half. That's my first part. Then I'll have 2 and 2. This is A, and this is B. Now when I take A, take the inverse and multiply it by B, it'll produce VA and VB in order, just like this. I believe I should already have this made. Three quarters, quarter, negative, negative quarter, and 0.5. That's right. Now look at number 2, 2 and 2. Now second matrix A, take the inverse, set it to -1, times matrix B. Produces 4.8 and 6.4. Volts. These are voltages. Mesh, we got currents. Nodal, we get voltages. That tells me that VA is 4.8 volts up here, and VB is 6.4 volts. Now we know what we needed to know to start off with. We need to find the current through the 4 ohm. Current here. Go ahead and get rid of these. We need to find this current, whichever direction it is. It's going to be this way because it's greater over here. Current will flow that way. I needed to find the voltage across the 20. I know that. It's just 6.4. Needed to find the power across the 2 ohm. And so that'll take a little bit of doing. We need to find the voltage across the 2 ohm. Voltage across the 2 ohm is just 4.8. So, first the current through the 4 ohm. The voltage across the 4 ohm, because VB turned out to be greater than VA, then this is true. So the voltage across here, it's the difference between the two in any case. But here it is VB minus VA because VB happened to be bigger. So 6.4 minus 4.8 gives the total voltage across this resistor as 1.6. 1.6 volts. That's the drop across this resistor. Now if we wanted to find current amperage is voltage divided by resistance. 1.6 divided by 4 gives 0.4 amps, or 400 milliamps. So the answer for A, 400 milliamps. Now part B said find the voltage across the 20 ohm. 20 ohm resistor, we're at 0, we climb to 6.4, voltage across it is 6.4. And now we know to find power across the 2 ohm and voltage across the 2 ohm. I'll just go ahead and write D down here. And D is 4.8. The voltage across the 2 ohm resistor is 4.8 volts. Now part C. C, I have the voltage across the 2 ohm, and I know that it's 2 ohms, so I can find current going this direction. 4.8 volts divided by 2 ohms gives 2.4 amps. Now if I have 2.4 amps there, and I have a voltage drop of 4.8, 2.4 amps times 4.8 volts gives me 11.52 watts for the power delivered to the 2 ohm. 11.52 watts. And there is question 2 solved. Question 3. Question 3 says to use superposition to find the voltage across R3. But if it didn't say to use superposition, what could I do? I wanted to find the voltage here. Well, I could take, so this is, I could turn this into a voltage source with a series resistance, and I could turn this into a current source with a parallel. Could do either or, either one. If I went with turning this into a voltage source, then I would have these two voltages in parallel. Yeah, in parallel. So what I would do here, if I were left to my own will, I would turn this into a current source, and then I would combine this current source with this one. They would be going the same direction, so they'd add up. It would be 2 amps, 24 divided by 12. So I would have 10 amps going up, and 12 and 24 parallel, which would probably give me something around like 9 ohms, likely. So then I'd have a single current source worth 10 amps and a single resistance, a Norton resistance of about 9, with this being RL, and we have a value for it. So it would end up being pretty simple, but it tells us to use superposition. So, process for superposition. If I wanted to, superposition uses it says that each individual source, these two sources, have their own contribution to the circuit individually, and they combine, they have their effects on each other that add to the total. And so what superposition does is it finds each contribution and adds it to the total just directly. But to do that, you have to remove, if I wanted to find the contribution of this guy to the circuit, I'd have to take this out. And if I wanted to find the contribution of this to the circuit, I'd have to take the voltage source out. To take out a current source, you remove it entirely. You pretend that it's gone. Open terminals over here. There's nothing here. And to find, if you wanted to remove the voltage source, you short it. Pretend that's a straight wire. There's no battery there, it's just a wire. So here is the circuit with the current source removed from the point of view of the battery. We leave the battery positive and we see 12 ohms. And then we get to this point, we look right, and there's nothing there. That's gone. but we keep going and we find a junction. We break two ways. We see 56 here and 24 here. And then they come back and combine on the other side and go back to the negative of the battery. So that is what the circuit looks like from the point of view of the voltage source. The current source, we have this shorted. We're going to come out of the source, go up, and we have a junction. We break two ways. See 12 on the left and nothing on the right. We'll have to trace that, but the 12 goes back to ground, back to our negative. And going the other direction, here we end up seeing another break with 56 and 24. And they recombine on the other side to that point. And then they all go back to ground. Now, you can see here that we have a combination circuit, series element, or you have this 12 in series with a parallel branch. Here you have these three parallel. So the current source is acting on a parallel circuit, and the voltage source is acting on a series circuit. And their combined efforts make this happen, make whatever results we are going to calculate out of this. We got to find a total resistance. Total resistance here, 1 over 24 plus 1 over 56, or product over sum. Gives us 16.8 ohms. Now 16.8 ohms plus 12 ohms equals 28.8. And so RT equals 28.8 for this circuit. For this one, we have 12, 56, and 24 all parallel. And we have a total resistance of 7. Now, we'll focus on the 24 right now. But with superposition, you want to isolate the thing that you want to find, because if you went to try and find everything, it'd be, you have to solve this circuit for everything, and then you have to solve this circuit for everything, and then combine and compare everything. But I'm only interested, we'll look ahead to see what we need to find. We need voltage across R3. And part A says what would the voltage be across R3 if it were the only one. So the effects of this circuit on R3. And then part B says what is the effect of the current source on R3, the individual effects, and that's what we're trying to solve for by nature of superposition. But then, so we need R3, 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 R3. It's all about R3, and then we have this part E that says convert into a voltage source. So that doesn't have anything to do with superposition. I'm only interested in R3, so that's all I'm going to solve for. To save myself some work. So I want to find the voltage across this. I have a total voltage and a total resistance. So total current, IT equals 24 volts divided by 28.8 ohms. And that is equal to 833 milliamps. Now, if that is the current, total current in the circuit, that means that 833 has to be going across the 12 ohm and through this section here. And that means that we have a voltage drop right there. 833 milliamps times 12 ohms gives a voltage drop of 10 volts right there. If we were at 24 volts here and we dropped 10, now we're at 14 volts at this point. And so if there's nothing else right here, we have to figure into the minus, subtracting it from 24. If there's nothing here, that means that the voltage across R3 is just 14. So 14, 0. So V3 equals 14 volts. And I'll draw it out like this just to stay familiar with the orientation. It is current's flowing this direction across it. It's positive over here, negative over here, or you can just look at the voltage of the battery. That's the only thing in here, and it's positive on the positive end of the battery, and it's 14 volts. Now over here, RT is 7, IT is 8, ET, total voltage, is equal to 8 amps times 7 ohms, and that's equal to 56 volts. Now if we have 56 volts total, and these are all in parallel, that means that the voltage across R3 is 56. And it's positive here. That means it'll be positive here on the left. And it's 56. So now we combine the effects. Oh, and that is the answer. Those are the answers to part A. Part A, this is the answer. Part B, this is the answer, 56. Now, part C says, what is the overall voltage? The true voltage of the resistor in this circuit. It's a comparison of the two. Lay them side by side. Superimpose the different values that we found. This is V3 or R3, and we have plus minus 14 here due to the voltage source, plus minus 56 due to the current source. They're in the same direction as each other. They're going to add up, and so 14 and 56, that's 6 and 10, 70. So V3 overall equals 70 volts. That's the answer to part C. Now part D says, based on the answer to part C, calculate power delivered to R3. So power, we have voltage and we have a resistance. That's all we know right now. Now what are the relations of power? Power is E squared over R, I squared times R, and E times I. So the direct way that I always do it, I would take this and divide it by 56 ohms and find a current. I'll do that real quick. I have 70 volts divided by 56 ohms, and I end up with this current, 1.25 amps. And then I multiply it back by 70 and have 87.5 watts. Or you could take, well, if I just found the current as 1.25, 1.25 squared times R, 56, give me 87.5 again. Or 70 squared divided by 56, 87.5. Either three method. These two are the more direct way. This is the more simple way using Watt's law that everybody knows. These will save your life if you don't know the resistance. Remember these. So power equals 87, what did I say, 87.3.5 watts. That's P3. Now we need to find part E. It says convert the 8 amp current source and R2 into a voltage source with a proper R2 placement and redraw the entire network with all values labeled. So I want to turn this R2 and the 8 amp source into a voltage source with a series resistance. So a source conversion, you know, the way that I'd have probably chosen to work this circuit to begin with. But let's see, what would I do if I wanted to turn this into a current source with a parallel resistance? I would draw these points right here. I would divide 24 by 12 and I would get 2 amps. I would have a 2 amp source going up. This isn't what the question's asking me to do, so you don't have to write this down, just pay attention. And then it would be 2 amps going up with a parallel resistor worth 12 ohms. And those points stayed right where they were. Now, if I wanted to turn this into a voltage source, this is kind of a strange placement. Might make you think that you can't do a source conversion on it, just the way that it looks. These are directly parallel, so you assume that you can. You know that you can actually. But what do? Make this thing look a little bit better. This, I can't erase this. This is printed, so. But I'll draw this point and this point. I need 2 points. There's 2 terminals on an equivalent circuit. Now, pretend that I erased this. This is an equivalent. You know, this is all one node if I were doing nodal. This is all the same place. So it doesn't matter how it looks, just as long as the connections are the same. So I'm going to change the way it looks to this. Now, I have 8 amps, and 24 ohms. Now I'll turn it into a voltage source by multiplying the two. 8 times 24, it's going to be a big number. 192 volts. It's a big battery. But this turns directly into, maintain your polarity. This is positive up here, negative down here. And it doesn't matter where you move the resistor. You can move it up top, move it down bottom. Just as long as the polarity of the battery stays the same. Positive, negative, positive, negative. This is now 192 volts and 24 ohms. And this is our equivalent of this. Now I need to take this and place it in here in place of this thing. So the new circuit would look like this. Just keep those points and there is my new circuit with this source converted to be a battery and a series resistance. And I've redrawn the entire network and labeled everything. So I would circle this. Now we have question 4. It says find the Norton equivalent. Now you need to find the resistance. If you want to find an equivalent circuit, first thing you need to do is, pretend that's gone, and you're looking for the resistance of the circuit with the sources removed. Here they're all current sources, so you're just going to yank them out directly. They're not going to be there anymore. There's nothing going to be in their place. They're just open circuits. So I remove this. It's now just open terminals. I remove this, and I remove this. And I want to find the resistance with this gone. If I wanted to measure resistance across this with this in here, I would actually be measuring 6.8 ohms parallel with the rest of the stuff, but take this out too. You want to find Thevenin resistance, don't want a resistor in there. Or Norton resistance, they're the same thing. But this new circuit, if I said this were point A and this were point B, I travel out of point A. I don't break into two ways because that's gone. I just see the 4.7. And then I go this way. I don't break two ways because that's gone. I see the 2K. And then I keep going. I get to ground. I don't care about ground. Ground is just a reference for 0 volts. I'm caring about point A and point B. Now I keep going and I end up here. And I don't go that way because that's gone. I see 8.2. And the total resistance, Thevenin resistance, Norton resistance of this circuit is just all these guys directly in series with each other. And so Thevenin equivalent resistance, Norton equivalent resistance, oh, 4.7 plus 2 plus 8.2 equals 14.9 kilo ohms. R Norton. Now I want to find the Norton equivalent voltage. Now to do that, I need to put all the sources back in. All the sources are back in there now. And a Norton equivalent circuit is a current source with a parallel resistance. And the Norton equivalent current, I probably said voltage, but Norton equivalent voltage, or the Norton equivalent current is the short circuit current. It's the current that would be flowing through this piece of wire if it's just a straight wire. There's no resistor here. So Thevenin equivalent voltage open circuit voltage. I Norton equals short circuit amperage current. Now, we have three sources in here, and let's see what it tells us to do. It doesn't tell us that we have to do anything in particular, nothing specific. So I can use whatever method I want to use to find the voltage across these points. And I want to look at this and see if I can do a source conversion. And it turns out that I can. I have these guys. I can, and it'll let me. I have these parallel, I have these parallel, and these parallel, and I can turn them into three different voltage sources. So that's what I'm going to do. I'm going to draw these two parts of the circuit, these two dots. And I'm going to multiply 10 milliamps by 2 kilo ohms, and I'll get 2 volts. 0.01 amps times 2,000 ohms, 20 volts. I'll get 20 volts. I'll redraw these points. And now I have a voltage over here. Oops. Redraw these points. They just move straight down. Let me fix that for you. So I just took these and moved them straight down. Multiplied these together and I ended up with 20 volts. I had this in parallel. Now it's going to be flipped up here to be in series. Or down bottom, it doesn't matter, it's still an equivalent circuit. 20 volts and 2 kilo ohms. The resistor stays the same, you just flip it up or down. Now I'm going to draw this point right here. and I'm going to multiply 8 milliamps, 0.08 0.008 times 4,700 ohms. End up with 37.6 volts. Oh, and note the polarities. This was positive because this was positive. And now our polarity here, we're positive on the left, so we're going to be positive on the left still. And it doesn't matter where you put the resistor, just as long as it's in series, because it's an equivalent circuit, a representation of something different. If it acts the same, it is the same for all that we care. 4.7K, and this was 37.6 volts. And now I'm going to draw these points. And this is RL. So this guy, we just took this between these points, turned into a series circuit. Took this, turned this into a series circuit between those points. I could have just drawn it, right here. It wouldn't matter. It's the same thing. Now here I'm going to take 8,200 ohms and multiply it by 4 milliamps. I end up with 32.8 volts. I'll put my resistor up there up top. Doesn't matter, but I need to make sure my polarity is the same. And it is 32.8 volts. And 8.2K. And this never changed. There is, if you want to see source conversions done like this, there you can get it done like this. I'll just go ahead and draw that. These are equivalent circuits. They're not at all the same. Like this circuit is not what it looks like. If you wanted to see this in person, anytime you see a current source is a bunch of electronic parts, because you can't have a steady current device irrespective of resistance out of a battery. You have to have some special things going on. So this is a representation of something bigger. This is a different representation of that something bigger. It's also going to function the exact same way that this thing will in any case. And if you put RL in here, it's like using a Norton or a Thevenin equivalent. If you build the circuit, you combine this thing in a way that what we're just about to do, it'll still be the same equivalent circuit. It'll act the same way, and it'll be the same for all that we care. You can build this circuit. You can build this circuit at home, but you can't build this circuit at home unless you knew what was going on here, because these are strange. Current sources are weird. So now we have these batteries, and they're all in series with each other. Just like I can combine current sources in parallel, I couldn't do that here because they're not in parallel. These two aren't, because this guy's in the way. But now I work them all out into a way that I have all my voltage sources in series. Now I can combine them. I'll look at my polarities. If I have batteries with their polarities in such a way like this, positive to negative, they're going to add on to each other. So the voltage between these 2 points, the voltage between these points is 32.8. Now if I didn't have these resistors in here to drop anything, or if this were an open circuit, voltage here is 32.8, voltage here is 32.8 plus 37.6. Now if I started here, the voltage at this point is 20, and the voltage at this point is 20, and the voltage here is 20. When I get here, it's 20 minus 37.6. If this is the probe that I'm working with, this is my positive end, I'm hooking it up to the negative of a greater source than 20. I'm going to read a negative voltage, and that's all a negative in a voltage is. It's just a reverse polarity. But you can combine these in series by, I'll work over here just because I have these guys adding and that guy subtracting. Rather do 2 additions than 2 subtractions, just for my bias. So I'll and look at the second sign that you see. If you're going around, if I'm going around counterclockwise like it just said I was going to, say plus 32.8 plus 37.6 minus 20. Or the inverse, I could go clockwise and I'd say plus 20 minus 37.6 minus 32.8. I'd end up with the same thing, but with different polarities. You know, it'd show a negative. It just means that your signs are flipped. You can just turn the thing around and it'd be right. So 32.8 plus 37.6 minus 20 equals 50.4 volts. So now I combine those together. I'm going to combine them and stick them right here. This isn't a source conversion, this is just an addition. This was 50.4 volts. This is 2 kilo ohms. This is 4.7 kilo ohms. RL and 8.2 K ohms. Now I'll take these resistors and combine them in series. And look what I've worked myself into, a Thevenin equivalent. I already know what it's going to be. It's going to be 14.9 thousand. 8.2 plus 4.7 plus 2, 14.9. And so I'll just grab another sheet of blank paper. .9 kilo ohms, 50.4 volts, and I'll just move my RL over here. See, I didn't include RL in that addition because I wanted to keep it separate. Thevenin equivalent circuit. But it asked us for a nodal. And we were trying to find short circuit current. That's where we left off before we ran off into the weeds. So we're one step away from a Norton equivalent. It doesn't matter how you get there. We went and turned it into we could have done super mesh on this, which wouldn't be much fun. 50.4 volts times 14,900 divided by, 50.4 volts divided by 14,900 is 3.383 milliamps. With the same resistor parallel now. Three point three 3.383 milliamps, 14.9 kilo ohms, and this is RL. So there's our Norton equivalent, and it gave us RL is 6.8K earlier on, but that doesn't matter for us yet. We've got a Norton equivalent. And then it says convert the Norton to a Thevenin and draw the Thevenin. Well, we did that backwards. We went and found our Thevenin first, turned it into a Norton. It doesn't matter which direction, which way you go, unless he tells you to use a certain method. And then there's easier ways of doing each. But now we need to use the equivalent networks to find the current through RL when it's 6.8K. So I'll just do this 6.8 kilo ohms. Now, if you weren't sure of yourself, okay, so we have a total resistance, these two in series, 14.9 plus 6.8 times 1,000, we have 21,700 ohms, 21.7K. That's RT. And then 50.4 volts divided by that number gives us this current. And that current is flowing down through RL. So I'll multiply this by 6.8K to get a voltage across RL of 15.794 volts. And it says, oh, that was part D. It said find the voltage across it. Part C says find the current through it. So there's the current through it. 2.323 2.323 milliamps equals IRL. Those are those two numbers. That is a 2. Or you could do it like this. You could say I have a total resistance parallel 1 over 1 over 14.9 plus 1 over 6.8 gives me 4.669, and then 4.669 times 0.003383. That many milliamps gives me a voltage. That should have been multiplied by 1000, so that many kiloohms, that many ohms. So 4,669 ohms times 3.383 milliamps. Uh, 3383. $15.796. 15.796. And current through it in this position is that divided by 6,800 gives 2.332 or 2.323 milliamps. Now I have this question E. It says, determine resistance of RL if it is receiving 42.6 watts of power. I like Thevenin's, so I'll stick with Thevenin. This was 14.9K and 50.4 volts. And this is now 42.6 watts. And I have some insider information. This question is flawed. It's supposed to tell you the current through the circuit. IT equals 1.69 amps. So if we have 1.69 amps flowing through the circuit, we have 1.69 amps across this resistor. And if we have, we now have a current and a wattage. And what is power? Power, we need a relation between wattage and amps, power and amps. And we do, but we're looking for resistance, right? Yeah. So this, you wouldn't need I squared R or anything because you're given a current. If you were given a resistance and a power, you would need those other relations. But here, you have a power and a current. What is power? It's I times E times I. So 42.6 watts divided by 1.69 amps equals a voltage of 21.73 volts. Now if we have 21.73 volts and 1.69 amps, we know resistance is just voltage divided by 1.69. That gives us that number. Okay, well, that would be true, but that is not the hold on. I've done something wrong. So this question is meant to give you current. Well, forget about it. It's a flawed question. It's supposed to give you more information. I wish you luck.